Okay, so you're turning in is that section 5, module 1, section 5? The whole thing, right? Everyone turned it in? So we're gonna talk about it. So it was something like this, right? We had a function that was our input to that function was the temperature in degrees Fahrenheit, and then the output of that function was the expected attendance at a sporting event. And so hopefully, graphing the function should be no problem. And then the graphing the point that's maneuverable, the movable point that's actually showing points on the graph, should have been no problem as well. And so what is, if we're using n, then to manipulate where that point on the graph is. All right, and so you don't want to think of this as like a bead on a wire. When you look at that blue graph, what does that consist of? We talked about this last time. What is it? It's lots and lots of points. Each point shows a temperature and a corresponding attendance, right? And so when you have this point that you can move, it's not that you're like sliding a bead on a wire. It's that you are highlighting one of those points, and then we can change which point we highlight. That's the way we think about it. Think about how we can change which point on that graph we're highlighting. Right now, it's showing 50 degrees, and the height is the corresponding temperature. So how do we graph that point then? How do we graph that point? What's the x-coordinate of the point? No, not 50 now. It's 26. Now it's 39. N, right? N. And then what's the y-coordinate of the point? Right, so if we want to get the exact point on the graph, we're going to use the function and get the output of the function when its input is n. So then we're gonna plot this NaN, right? So then you had a additional task here to come up with this triangle that shows a change in temperature of 10 degrees and the associated change in attendance. Okay, and so how do we do that? Well, let's start with this horizontal line. So it's a horizontal segment. So it's no different than graphing the a function and then limiting it from 0 to 110 degrees, like the way you did that, right? You graphed the a function and you limited it from 0 to 110. So this, you think of it just as a whole horizontal line that we're going to limit it with a starting and ending value. Okay? So how do we graph a horizontal line? With like a constant value, x value or y value? What were you going to say?
Y value? I mean,
yeah.
Oh, it's a then, y equals a then.
Okay, so it's a y value, right? So a horizontal line means a constant y value. So the equation will be y equals something, right? So what something do we want? So the final product is on the right. I'm going to kind of build it over here on the left. So we want y equals. What y value do we have? And it's going to be just the y value of the point, right? Which we said was right there, a of n. Okay, a good start. So that's that whole line. But then we want to only show it from a certain, starting x value to a certain finishing x value. What's the starting x value of our segment? It starts at n, right? It starts at n, and it ends at 10 degrees later, n plus 10. So we're going to go n less than or equal to x. And that gets it. Okay, so horizontal lines are y equals and we want that y value at the point. And then we want to start at the point, so that's the x value of n. We want it to end at the x value n plus 10. Okay, now we need this segment here. We want to draw, so think of that, instead of thinking of that as a segment, think of it as a whole line that we're just going to just show a piece of a whole line. It's a vertical line. How do we represent a vertical line? X equals. So now the question is, what x value is that? What was the x value of our point? N. What x value is over here? It's not going to be n, right? It's going to be, it's over to the right. N plus 10. The x value of that vertical line is n plus 10. And the same thing now, we just want to take a piece of that. The piece starting at n. So it's starting at a certain lower y value, right? What y value is that? A of n. And then we want to go up to and stop at the y value at the point on the graph, at n plus 10. So this is our a of ny value, and then looking at that point right there, its y value is a of n plus 10. So we're going to go from a of n less than or equal to, we're restricting what? Y values now, right? We're restricting y values. So we want the starting value, the y value at that point, which is a of n. The ending y value we want to be the y value of that point in the graph, which is the output when the input is n plus 10. So we're going to go up to a of n plus 10. And there it is. Okay, so figuring out these values, both x values and y values, using the function is going to be a crucial skill you're going to need when we get into the calculus. Okay, so being able to come up with these two statement lines to represent these segments and represent values, like I said, these segments are made up of values that are x values and y values using n and using the function. And so this is going to be something we're going to do a lot. When things get complicated, this needs to be in place. This needs to be no problem, so that you're not getting tripped up on something like this when we're in the calculus, it's getting hard. Questions on that? So for time's sake, I'm not going to talk about what happens over here when the function's decreasing. If you want to talk about that further, I can stick around a moment after class. But this is the general idea of creating that triangle that you can now change as you change n. Any questions on that? Last chance. Okay, let's see if you get it. Here's a quiz. Read carefully. Put GC away. So just all you need is something to write with. No calculator, just something to write with. Anyone got one? Who doesn't have one? Okay, read carefully. Read very carefully.
coordinates of point P. This is point P. And here's the coordinates. Ordered there. Right, ordered. Oh, okay, sorry.
Okay, one more minute. 1 minute. Okay, finish up what you're writing. Last chance. Okay, get out something else. You're going to grade your own. Get out something else to write with. Okay, ready. So you're on your honor. Don't change your answers. Grade honestly. Here we go. So how are we going to represent segment S? Segment S. It's going to be y equals or x equals?
Y equals.
Y equals, that's 1 point. If you put y equals, 1 point. What y value do we need for that segment? F of C. F of C. Okay, that's 1 point. F of C is 1 point. Are we done?
No.
That's all. That's the whole line. We need the segment. So it's going to start at A. It starts at the x value A. So if you had A and B, that's a point. If you had A and B. If you had x, that's the 4th point. So this is worth 4 points. Y equals is a point. F of C is a point. The A and B endpoints is a point. And that you had x, that's a point. So 4 points for number 1.
I had A and B, but I wrote F of A, F of B.
That's not right. Yeah, it's got to be A and B. It's got to be A and B. F into A and F of B are y values. Okay. All right. Coordinates of point P are x coordinate is C. Y coordinate is F of B. 2 points. The x coordinate is C, but its y coordinate is the y coordinate of the function at B. Do you see it? Where is C F of C? That's the point on the function. You need C F of B. Does it make sense? This is a really important skill that you have to have. using the function to create coordinates. Okay?
What did you write B equal that second?
What's that?
What's that second word B? What?
C f of b. C f of b. Is parentheses throwing you off?
Oh, okay. Good.
C f of b. Okay? And then your arrow that will indicate, or where would you look to find the value of f of a? Okay? The arrow, you would not point the arrow at that point. You would point the arrow at the y-axis. Right there. 2 points, all or nothing. If you point it at the point, that's not correct. You're looking for the value. The value of f of a is going to be indicated on the axes. So you're pointing at the axes, all or nothing. Okay? Total up your score. So far, there are 8 points possible, right? 1, 2, 3, 4, 5, 6, 7, 8. And then once you got that score, then add 2. Everyone gets 2 points for free. Add 2 more, and it's out of 10. Does it make sense? Put your score at a 10, and then just for time's sake, just hold on to it and just leave them on your desk, and we'll pick them up when you're done. So, or just no, we'll pass them up. Pass them up.
I was debating between
Or-
on the one and three.
Okay, so more important than you got a good score on this is that if you didn't, you corrected your thinking. You corrected your thinking. Did this help to clarify?
Yes.
So, does anybody have a question about why an answer is what it is?
Yeah.
Okay. Do we have all of them? Yeah.
I just want to know, you're
Sure.
gonna put that up on the blackboard?
What's that?
You're gonna put that up on the blackboard?
I hadn't planned on it, but I can give it to Stacey if you want. You'll get this back. You
Oh, okay.
get this back after it's recorded. Okay. So, have you talked about relative size in this class? Oh, someone said division. Okay, that's a good sign. And have you done any bar diagrams? Has she done these things at all? Okay, so this is just an illustration, a way to illustrate the value of two quantities taken together. So when I say quantity A, I'm talking about like height of something, or amount of time that's gone by, or weight of something, quantity A. And then quantity B is something else, like the area of something, or the temperature of something. Okay? And then the length of the bar then is just representing the value of the quantity. So we're taking these two together. So maybe this is amount of time that has gone by and a distance traveled. And so the length of that top bar is an amount of time, and the length of that lower bar is at a distance traveled. Okay? So relative size. So what is the relative size of A with respect to B, or the relative size of A to B? Meaning, how big is A using B as a measuring stick? Have you done something like this?
A and B.
What's that?
A over B.
Okay, so first of all, A and B are not values. They're like things like height, weight. So it's not a value. But I'm asking you to estimate it based on the length of the bars. I'm asking you to estimate what that relative size is. Everyone think to yourself, what do you suppose that is?
Is B like 1.2 A?
Okay, she said B is 1.2 of A. Is that the relative size of A to B?
I say A is 4/5 of B.
4/5. Something like that? Yeah, 3/4, 4/5. So I said 0.8 or close to that. Okay, now I'm going to tell you what those values are. 18 and 23. So can you create an exact representation now of the relative size of A to B? Can you create an exact representation, mathematical representation of that value? What would it be? How would you come up with an expression that would give us that relative size exactly? Yeah.
18 over 23.
He wants 18 over 23. Yeah, it's a quotient, right? Relative size is a quotient. It's going to be if we're measuring 18, or the quantity A with respect to quantity B, then that quotient, 18/23, in this case that's something like 0.78. Okay, why divide? What's the nuts and bolts behind how does division give us relative size? So you may have talked about this. So it's basically 18/23. So 23rd is 1/23 of the quantity B. Think of 1/23. Then quantity A is 18 of those, right? So we're taking 18 1/23 of B. We're taking 18 1/23 of B. And to take 18 1/23, you divide. 18 divided by 23. Okay, and that is about 0.783. Okay. So then suppose this relative size is maintained as B changes. So the value of B is going to change and the relative size is going to be maintained. How would you find the new value of A?
18/23 times B.
He says 18/23 times B.
The new B value is multiplied by 0.783.
Okay, so they're saying the same thing, right? It's to be the new B value times 18/23 or 0.783, which should make sense because if A is the size, if 18 is this 18/23 is how big A is relative to B, it's 18/23 of B. When you knew what B was, you'd take 18/23 of it to get A. So, and that's multiplication, right? That's multiplication. Okay. So here, do it again. Tell the person next to you. Estimate the relative size of A to B. Go. Size of A relative to B. Little bit more than 2. Did you come up with like 2 1/4, 2.2, 2.1, something like that? A little bit more than 2. Okay, I'm going to give you the numbers. Okay, what would an exact representation of that relative size be now? So now we can get it exactly. Which would be? I hear a lot of you saying 35/16. So that quotient gives us the relative size, the size of A relative to B. And that's about 2.19. Okay, so now that size is going to be maintained as B changes. How would you get the new value of A? How would you get the new value of A? Yeah?
Multiply B by 35/16.
Right, whatever B you have, the relative size of A is 35/16 of it. So you're going to multiply. One more. This is the relative size of B to A. The relative size of B with respect to A. Go. Okay. If you said 1/5, 1/6, you're in the ballpark. Okay?
B to A.
This is B to A now, the size of B relative to A. Okay? Exact representation will be 3.6 divided by 0.59 or 0.59 divided by 3.6. Second one, right? Second one. Okay? About 0.164, which is close to 1/6. Okay? So now, as we have some new value of A, and we want the value of B. So we're just going to take 0.164 or 0.59 over 3.6 times the value of A, because that's the size of B. That's how big B is relative to what A is. So you're going to take that fraction of it to get the new value of B. So what do you notice about... So in this number then is called a constant multiple. Because if the relative size of A and B is maintained, this thing stays constant, right? This stays constant. Given any value of A, you'd use that same constant to get the value of B. So what do you notice about the relative size and the constant multiple? Oh, that was an easy one. They're the same, right? So the relative size becomes the constant multiple as long as you are starting with A and you want B. Then it's the number you multiply A by to get B. So it's the same. Okay, that's important. Okay, any questions on this? Okay, so here's a quantity A and a quantity B. And now I'm showing you the actual values of those. So the value of quantity A is X, and it's increasing. The value of quantity B is Y, and it's increasing. Okay? Is the relative size maintained? Is the relative size maintained? And what? So if the relative size from Y to X is maintained, then Y over X is a constant. Agree with that? What would you estimate that constant to be? So this is what? This is the relative size of quantity B to quantity A.
1/3.
1/3. Is it 1/3?
Say from B to A or A to B.
B, the size of B relative to A. 3, right? 3. It's not so. It's the size of B relative to A is 3. So that ratio, no matter what the current value of X is, that ratio stays at 3. Okay, what about delta Y and delta X? If I took some change in X, would I have the size of delta Y to delta X? Would that be maintained? Have you seen this symbol yet?
Yeah.
Oh, we did. Yeah. So I showed it with you last time. So delta X meaning some change in X and some change in Y. Yeah, I think that. So I think it's pretty clear that follows along, right? That if your actual quantities maintain this constant ratio, then if you took any change in X, you would get the same relative change in Y, which would be 3 times as much. Okay? So K equals 3. So Y increases 3 times as fast as X for all X. Would you buy that? That Y is increasing 3 times as fast as X for all X. So is this constant rate of change? Constant rate of change?
Yes.
Yeah, because it's Y is increasing 3 times as fast as X, and that constant rate of change is 3. Questions on that? What do you think? Okay, so now I got another one for you. So tell the person next to you, how's this different? What's going on here? How's this different than what we've been talking about so far? Go. Is the size of Y relative to X maintained? Clearly not. X starts out less than Y. Now X is about equal to Y. And then X is greater than Y. So there's no way that the quotient of Y to X could be a constant. All right, well, let me give you another perspective on these exact same bars. Same 2 quantities. So this is an identical situation, but I'm just giving you a different perspective on it, okay? So this is the same quantities, A and B, X and Y increasing together the exact same way. But now I'm showing you a different perspective on that. Let me turn the top one off. It's not distracting. So the length of bar X and the length of bar Y increasing together is exactly the same as what I showed you before. I just moved the top bar back, and now I'm highlighting the change starting from where the animation starts. I'm highlighting that change in red. So now, is the size of delta y relative to delta x maintained? Okay, what do you think that relative size is? I'm hearing people say a half. The size of delta y relative to delta x is a half. Agree with that? Yeah. Okay, so go back to the original one. So this is the same one. We know that y over x is not constant, but delta y over delta x is constant at 1/2. So y is increasing half as fast as x. Would you buy that? That y is increasing half as fast as x for all x.
Yes.
Most people are nodding, saying yes. Okay, here's the $100,000 question. Does y change at a constant rate with respect to x? Talk to the person next to you. Yes or no? Yes or no?
Because I think you're going to bear like with an index of security.
Okay, so before we discuss it, so let's just take a vote. So how many people think yes? And how many people think no? Or you don't want to admit? What about the rest of you? Not sure. Okay, let me give you, so before we actually answer that, let me give you that same thing shown a different way. So here's that same situation, okay? So it's smaller and thinner, but so we got that, the value, the x value at the bottom and the y value at the top. And this is the same two quantities changing the same together, just as we had before. So we said this was the y value, right? And so the y value is shown vertically, right? So I'm going to take that y bar and I'm going to turn it vertical, like we show y values on graphs. And keep those bars increasing together the exact same way. Okay? Now I'm going to turn on, so this point then would be every x, the coordinates of that point would be every x and corresponding y, right? From those two bars increasing together, right? So I'm going to turn on all such points, right? So it's like the trail that one point at the top of the bar leaves a trail, right? I'm going to turn it on. And I'll ask the question again. Are y and x in a constant rate of change relationship?
Yes.
Talk. So does this change your mind? Go.
So linear line.
Yes. But no way.
The relationship is
Do the values of y and x maintain a relative size? The values of y and x. The values of y and x, do they maintain the relative size? They don't. We said that before, right? X is less, and then it's equal to, and then it's greater. Right? What about the change in y to the change in x? Relative size is maintained, right? Do we have constant rate of change or not? Yes. Constant rate of change. Why? Because these two quantities graphed in the xy plane all those points would produce a line. And that's linearity is equivalent to constant rate of change. So what is the test for whether you have constant rate of change or not? Is it looking at the quantities themselves? No, we saw one example where, yeah, you had a constant ratio of the actual x and y values. Here we don't. So what is the actual test? Changes, right? So if I give you a change of x, say this much, call it delta x1. How much will y change accordingly? So what is delta y1? How much did y change when I changed x that much? 1/2 of my change in x, right? Different change in x, call it delta x2. How much did y change when I changed x by that much? Okay, so, right, 1/2 the change in x2. So it's this proportionality of the changes that produces constant rate of change. Not necessarily that you have to have proportionality of the values themselves. Because here they are not, y is not proportional to x. But the changes are, and that's why you get constant rate of change. And that's why the points, so it's like these triangles are all going to have the same shape, no matter how small or big they are. They're all going to have the same shape, which means the points fall in a straight line, right? The points are going to fall in a straight line. So let's just summarize this. Constant rate of change. So let quantities A and B be represented by variables x and y respectively. B varies at a constant rate of change with respect to A. Means proportionality of what quantities? Proportionality of the changes in x and y. Or in other, the changes in B are proportional changes in A. So these are equivalent statements. If you have two quantities whose changes are proportional, that's equivalent to saying those quantities are in constant rate of change. Or exhibit constant rate of change. So now there's two mathematical results to this. And the first is that the ratio, the quotient of the changes is a constant. The relative size of the change in y to the change in x stays the same. And then we saw, so then what if you knew the change in x? How could you get the change in y? So we talked about this earlier. So you know the value of one quantity. The relative size is maintained. How do you get the value of the other quantity?
Multiply the change of quantities.
Multiply, right? So you just multiply by that constant, and it'll give you the corresponding change in the other quantity. So that first one is saying that the size of delta y relative to delta x is constant. And the second one is saying that the change in y is a constant multiple of the change in x. Okay, in this example, so what's the value of k? What is the relative size of the change in y to the change in x? In this example, what is it? A half, right? And what is the constant multiple that would give you a change in y, given the change in x?
0.5.
A half. They're both a half, right? That's what we said. The relative size is the constant multiple. Okay, and so that also applies here when we're talking about comparing the changes. Okay, first example we did. What was the relative size of the change in y to the change in x? Given any change in x, what was the relative size of the change in y? 3. And if you knew the change in x, how would you calculate the corresponding change in y?
3 times.
Multiply by 3. Multiply by 3. So this is the proportionality of the changes. That's the essence of constant rate of change. And then here's the mathematics of it. Here's the mathematics of it. That the ratio of the changes is a constant. And that constant, if multiplied by a change in x, would give you the corresponding change in y. That's the mathematics behind it. Okay, so let's keep that. We'll just keep that in the forefront. So this is what what we have, and now we got to apply this to the real world. So how does this apply? So these may seem like really simple situations that you could figure out, but our goal is to symbolize them or model them with the mathematics that we're talking about, right? With these delta symbols and k and all that stuff. So we take an easy situation and see how it can be modeled by this notation. That's a crucial skill that you need to have. Okay. So we have a trail mix, costs $2.75 per pound, which means that the cost in dollars is always 2.75 times the number of pounds that you buy. Agree with that? Makes sense, right? Okay, so in this situation, define each variable below completely and precisely, so that there's no question what exactly you mean by x. You got to be specific, and you got to have units. Okay, go try this. Work together.
K is the cost. K is the 2.75. It's important to have dot output. Yeah.
Right, number of pounds is actually pounds of weight. So number of pounds is y by 1 pound. Price in dollars.
Is it like is why that symbol like the price with the input certain amount of pounds? But I don't think it's just price. Like I think we have to elaborate. It's like why is right? So like if you like function number of pounds.
Okay, what is x? Number of pounds of mix. Number of pounds of mix. Or you could have said the weight of the mix in pounds. Y is corresponding cost in dollars. So what would delta x be? A change in the number of pounds. A change in the number of pounds. And delta y? Then the change in the cost. Okay, and what is k? 2.75. So I should have been more specific here. Constant rate of change of what? Of? Yeah, of dollars or of cost with respect to weight. What are the units on the 2.75? Dollars per pound. So that follows right here. Delta y is the amount of dollars, delta x is the amount of pounds. So dollars per pound is our value of k. So suppose we had a situation and we wanted to compute the constant rate of change. Write an expression using these symbols that would compute the constant rate of change. Or tell the person next to you what expression using those symbols would compute the constant rate of change. So sometimes in scenarios you have to come up with it yourself. Write an expression that would do it, that would compute the constant rate of change. Yep, in this case we compute 2.75. Yeah. What would it be? Yep. Oops, sorry. So that last one was this. You should have said this. Delta y over delta x. Okay? Write an expression using these variables that computes the change in cost given the change in number of pounds. So you know how many pounds you have, and you want to calculate the change in cost. What expression would you use to do that?
Which we can Y
Yeah, okay, so then we need delta y.
we don't want to want us to write a function that
So how would we get delta y? Delta y would be
Right, but you can also just use that equation. Delta minus
2.75
and then we know delta
times your given change in x.
so then you can solve for delta.
Okay, so it seems really easy. The reason it seems really the reason it's easy is because I'm holding your hand. I'm holding your hand. The key is, if you just have a situation, can you take the initiative to set up your variables, and know how to answer questions like this without being prompted, the way that I'm prompting you, okay? All right, so after scooping some mix into your bag, you decide you want to buy some more. The additional cost you pay for 1.5 more pounds of trail mix is 2.75 times $1.5. Identify what these are in this situation, delta x, delta y, and k. Go.
Yeah. Yeah, oh yeah, because it's the additional column.
Yeah. And then,
Delta y is the number of fourth column
yeah.
What is delta x? Someone said 1.5. Is it right? 1.5 pounds, right. What's delta y? K delta x. Units? Dollars. And what was K? Still 2.75. Any questions on that? One more example, and we'll be done. Next, you remove 0.4 pounds from your bag and return it to the bin. When no one's looking. Go. What is delta x? What's delta y? What's k? Okay, a little bit different. What's delta x? Okay, I heard a couple people say it. Here's the key, negative 0.4. Mathematically, a change, if it's a decrease, mathematically, then that's a negative change. Final value of the quantity minus the initial value of the quantity will give you a negative number. Okay? So what's delta y? And so we'll get a negative. Does it make sense? We'll get a negative value. Because?
Taking power out.
But this is about your cost, right? It makes sense that delta y is negative. Because your cost went down. Your cost went down when the pounds went down. Okay? K is positive or negative 2.75? Still positive. Okay, I think you have some cards to do. Is that right? I forgot on Monday.
Yes.
Just do some card. And is it the major takeaway of the day? Is that